High-frequency electromagnetic waves are invisible, continuous, and highly unpredictable when they interact with complex geometries in 3D space. Predicting these multidimensional wave interactions requires mathematically arduous calculations. Traditionally, engineers bypassed this mathematical wall by physically building hardware prototypes and testing them in laboratory environments. But fabricating, testing, and inevitably rebuilding these prototypes requires time and material costs that rapidly outpace modern product cycles. To engineer modern RF systems efficiently, you have to accurately predict real-world electromagnetic behaviors entirely within a digital environment before any physical hardware is manufactured. Ansys HFSS is a comprehensive industry-standard simulation tool built strictly for 3D electromagnetic field analysis. It avoids relying on simplified high-frequency approximations to guess how a system will perform. Instead, it operates as a full wave solver. That means the software directly simulates Maxwell's equations across an entire volume, accounting for absolutely all electromagnetic interactions within a given environment. This level of precision is achieved through a rigorous mathematical engine that systematically translates continuous physics into a solvable computational environment. The primary bottleneck in computer science is that processors cannot natively calculate continuous physical waves. They only process discrete numbers. HFSS bridges this gap using the finite element method. This mathematical engine begins by taking a complex 3D structure and the continuous space surrounding it and dividing it up. The software shatters this continuous environment into a massive grid of small, discrete geometric shapes, specifically tetrahedra. The full wave solver then isolates a single tetrahedron and calculates precise electromagnetic field vectors strictly within those isolated boundaries. The software then stitches the individual mathematical calculations of all adjacent tetrahedra back together to approximate the continuous field. The finite element method resolves seemingly impossible calculus by reducing the continuous physical world into a structured system of simultaneous algebraic equations. The physical reality of this method is that achieving high fidelity requires incredibly dense grids, often utilizing millions of individual tetrahedra. Processing millions of algebraic equations demands immense hardware power and time. To resolve this resource tension, HFSS relies on automated adaptive meshing. The mechanism evaluates a passing electromagnetic wave as it moves through the structure. The software automatically subdivides the mesh into much smaller, denser tetrahedra, exclusively in regions with steep electromagnetic gradients or complex geometry. Regions of empty space or low complexity remain coarse and unrefined to save processing power. This dynamic refinement runs automatically, constantly balancing simulation accuracy with the computational load. Adaptive meshing makes full wave solving practically viable, applying heavy processing power exactly and only where the physics require it most. With the mathematical engine operating smoothly, the focus shifts to its primary engineering application, designing high-frequency hardware. This environment is routinely used to simulate low-profile microstrip antennas and array antennas requiring high gain. Engineers run these simulations to optimize performance metrics, including impedance matching, bandwidth, and radiation patterns. To test these metrics, HFSS utilizes parametric design capabilities, allowing engineers to instantly alter physical variables within the simulation. This visualization shows a schematic of a microstrip antenna on the left, mapped to its 3D radiation pattern plot on the right. Altering a single physical dimension directly impacts the resulting electromagnetic output. Structural changes immediately trigger a recalculation of the finite element grid, updating the results and reshaping the radiation pattern. This allows for the continuous exploration of various designs under realistic operating conditions. Parametric design lets engineers test thousands of structural variations and achieve ideal directivity before stepping foot inside a physical lab. While antennas are designed to radiate waves outward, the full wave solver is equally vital for trapping and routing digital signals inward on a circuit board. Maintaining signal integrity is a critical challenge in the dense, multi-layer printed circuit boards that form the backbone of modern electronics. As high-speed signals travel through a PCB, they generate unintended electromagnetic fields. This leads to physical layer failures like crosstalk, where invisible electromagnetic radiation from one active trace leaks over and corrupts data on an adjacent trace. Another failure is wave reflection, When a poor-me-matched component acts like a wall, it sends the signal bouncing backward along the line. Standard electrical schematic diagrams cannot predict these complex physical space parasitic interactions. By applying a 3D full-wave solver directly to the PCB architecture, HFSS functions as a vital diagnostic tool that catches catastrophic hardware failures before manufacturing begins. Ultimately, HFSS unifies the physical accuracy of the finite element method with the operational efficiency of adaptive meshing. Operating the software does have constraints. It demands a steep learning curve from engineers, requiring a deep mathematical grasp of electromagnetic theory. It also carries an intense resource dependency, requiring exceptionally powerful local hardware to process the simulations. The primary technological vector aimed at solving this hardware bottleneck is the shift to cloud-based computing solutions. Migrating full-wave solvers to the cloud will offer scalable, accessible processing options that bypass local hardware limitations. This also supports the integration of AI-driven algorithms designed to predict and accelerate mesh refinement even faster than current adaptive models. Modern high-frequency engineering demands mastery over the computationally rigorous engines that allow us to simulate reality before the first piece of hardware is ever built.